Good morning, welcome to
FunMath number 17.
FunMath17. This was really supposed to be minute math from yesterday. This is a very difficult problem from the AMC 12, I think, which means it's a contest for high school kids. And I think this was one of the problems near the end. I think the American Mathematical Association said only 2% of the people got this problem right.
Whoa.
So I was actually going to skip it yesterday, but then I realized you were making these chemistry models. So what are some of the models you have here?
Magnesium chloride.
Magnesium chloride. Okay, that's interesting.
I've got carbon dioxide.
Carbon dioxide. Cool.
Well,
all right, and what do you got there?
Carbon and water.
Carbon and water. Cool. So we were making little chemical models out of spheres, and turned out the problem was about spheres. 3 mutually tangent spheres of radius 1 rest on a plane. A sphere of radius 2 rests on them, or on top of them, I probably should have written. What is the distance from the plane to the top of the large sphere? So here's our situation. We have 3 small spheres of radius 1 on a plane, which is pretending to be my hand. And then we have another sphere on top of them. Okay?
Yep.
Now, as I said, this is a difficult 3-dimensional geometry problem. I don't expect you to understand all of this. But I'm going to show you how to solve this problem because it's actually pretty neat, and since we're making these chemistry models, it's kind of similar to what you were doing anyway. Okay, so do you understand the picture? Because I gotta use 2 hands here.
Yeah, this looks like ammonia.
Okay, here. It does actually kind of look like ammonia. It's not quite ammonia, but go ahead, hold on to it. Okay, so we have, looking at the centers of these spheres, we have, actually, sorry, I'm going to draw it this way. I'm going to draw the centers of my 3 little spheres as if we're looking right down on top of it. Okay, so we're looking from right down up here, straight down, and the center of the big sphere is up here. Okay, so I have kind of a pyramid if I look at the centers of the spheres. Okay, and the distance from the centers of the small spheres is 2. And the reason that is each of these small spheres has a radius of 1. So I go from the center to the edge, and then from the edge to the center. So I go a distance of 2. Does that make sense?
Yeah.
Yeah? Okay, good. And then the distance from the center of the small sphere to the center of the big sphere is, well, I go out 1 and then up 2, because the big sphere has a radius of 2, right?
Yeah.
Okay, awesome. So that's 3, because 2 plus 1 is?
3.
3! Okay? You can put that down if you want. Okay, and then what we're trying to figure out is how tall is this pyramid that we're looking at? Because we know we've got, here's the plane, here's our little spheres, and then here's our big sphere. We know we go up 1, then we go up some distance to the middle, and then we go up 2. 1, 2, question mark. But the question mark is our little pyramid. So all we have to do is figure out how tall this pyramid is. Okay? So that's the hard part of the problem, figuring out how tall the pyramid is. So if we draw the pyramid a slightly different way, this is 2, 3, 3, 3, 2, 2. So now we're looking, this is the top. And I drop something down to the middle here. That's the height we're trying to figure out. Okay? When I drop something down from the top, it lands in the middle of an equilateral triangle. And it's right in the middle. This is the hard thing that you don't know, how to figure out where the middle is. It turns out the middle is 1/3 up here. It's 1/3 of this distance, this whole distance. But we can figure that out because we have a right triangle. If this is 2, half the distance is 1. 2, and then question mark. We use the Pythagorean theorem. Let me call it x. Okay? The Pythagorean theorem says 1 squared plus x squared equals 2 squared. Do you remember the Pythagorean theorem?
Yeah.
Okay? For a right triangle, side squared plus side squared equals hypotenuse squared. Or 1 plus x squared equals, what's 2 squared?
4.
4. X squared equals?
3.
3.
So it's the square root of 3.
X is the square root of 3. So in our equilateral triangle, which is the base here, it's hard to draw the 3 dimensions, this whole thing is the square root of 3. And I said the center is 1/3 up. That means this is square root of 3 over 3. And this side is 2 square root of 3 over 3. Those are my fractions. That's the hard part. Now we have the easy part. Okay? I know, for example, that I have a right triangle here now. Goes up 3, goes across 2 square root of 3 over 3, and then height. Okay, so let me draw that. 3, 2 square root of 3 over 3, and then height. That's what we're trying to solve for. Okay, so I have a right triangle. What equation do I use with my right triangle?
Use the Pythagorean theorem again.
Right, so I have 3 squared, the hypotenuse squared, is 2 times the square root of 3 over 3 squared, plus h squared. Okay, 3 squared is?
It's 9.
9. This is 4 times 3 over 9. 2 squared, square root of 3 squared is 3. 3 squared is 9. That simplifies, but we'll get to that in a second. Plus h squared. 3 divided by 9 is?
3.
3 divided by 9 is?
1/3.
1/3. So this is 4/3. How many thirds is 9?
9 is 27 thirds.
Okay, 27 thirds. What is 27 thirds minus 4 thirds?
It's 23 thirds.
23 thirds equals h squared. So h is the square root of 23 thirds. There's my height. Okay, now let's go back to our model. So with our model, we have the height of the top sphere is the height up to the middle of the little spheres, which is 1. Remember the little spheres had radius 1. Then we have to go up from the center of these spheres to the center of this sphere, which was our pyramid. That pyramid has height the square root of 23 over 3.
Yeah.
Then we have to go up to the top. And how when you go from the center of this sphere up to the top, how far is that?
The center
of the big sphere.
That's the radius.
That's the radius, which was
2.
2. So I have 3, 1 plus 2, plus the square root of 23 over 3. The square root of the whole thing, 23 over 3. Cool, right?
Yeah.
So we actually, using math, can figure out how tall this is. And this kind of looks like a molecule. So maybe this three-dimensional geometry isn't just for playing around for high school kids in math contests. Maybe it helps you figure out something about molecules. And when they fall down. Ah! All right? Pretty neat, right?
Yeah.
Good job. Good job. That's a tough problem, but it shows you some neat stuff about three-dimensional geometry. And it also shows you a really cool problem that only 2% of the people got right. Can you believe that?
Whoa.
Whoa. All right, good job today.